Welcome to the second part of this webinar series. We'll talk about BIM and computational design. The merger of the two has been made possible by the integration of generative components and ecosystem building designer by Bentley Systems. Computational design is like writing an algorithm or script for your design intent. It is like writing a code for your building with all the design parameters being defined as variables. Generative components is already an established tool in the market for parametric designs, and the good news is that now it has been integrated into Bentley's BIM solution, Ecosystem Building Designer. At one point or other, we all must have drawn simple flowcharts for step-by-step logical instructions. Generative components workflow is based on the same concept of a sequence of transactions. The power of computational design is thoroughly leveraged by generative components, and we can explore infinite options of designs which cannot be imagined with a naked mind. The merger of generative components and Bentley's BIM solution has opened the doors to a tremendous potential of optioneering building elements. Let us explore some scenarios.
We start with an empty plot with defined side offsets and height limitations. We create a conceptual mass, the dimensions of which are controlled by parameters. We add some aesthetic cuts, and the offsets of the cut are controlled again by the design parameters in the control panel. Then we add the floors with parametric floor to floor height, and these floors are ABD or BIM elements with all the metadata associated with them, as you can see here in the catalog type and item categories. Then we export the floor areas to an Excel sheet and analyze if we have achieved the permissible areas. We can do this iteratively, changing the design using control parameters and exporting it again and again, analyzing the areas. So now we add solid walls at the back faces. These walls have to be responding to the change in the dimensions of the underlying mass. Again, these are ABD or BIM elements with all the properties or metadata associated with them. Then we add some curtain panels on the trimmed front faces. These curtain panels again are responding to the change in the design parameters in the control panel. If we change the offsets of the entrance void, the design of the curtain wall is updated accordingly. Now we add a curvilinear path which is leading to the plot boundary. It's based on this BSP line, which is controlled by its control points. The dimensions of this structure and the spacing of the panels is completely parametric. As you can see that we can adjust the parameters, the design parameters from the control panel, and change the spacing of the panels and the dimensions of the structure. Or let us say that we want to create a curvilinear pathway connecting the porch with an adjacent building. We can create a surface based on the base spline curve and divide the surface into parametric polygons. These polygons can also act as placeholders for customized panel designs, and we can use the same technique for facade optimization of buildings. Then we can start laying out the columns along the curvature of the pathway. We may not worry about the number of columns at present or the spacing of the columns, as these are parametric values and can be dynamically changed anytime during the design process. Now we will add the design grids to this curvilinear structure. The new grid feature enables us to sketch freeform grids in different axes. We can pick a spline curve to create a curvilinear grid, or we can draw the grids using the line tool. The labels at the ends can be toggled as required. So this way we can create quite an advanced design grid. That was about simple buildings, normal box type buildings. Now let us see a simple case of a curvilinear tower. In this case, the floor plates of the tower are elliptical in shape, and we are controlling the radii of the ellipses, that is the primary and secondary axis radii of the ellipses, using the law curve tool. We are simply connecting the dimensions of each floor plate with the law curve control points, and this allows us to control parametrically the silhouette of the building. Here is another version of the same concept. It is as if you are actually sculpting the skin of the building. And then, of course, we can use the solar analysis tool for performing shadow studies and solar exposure calculations. Let's take the example of a stadium seating. The sectional layout has to follow some rules of spectator sightlines. The step size of each row generally follows a parabolic curve, which is derived by a set of formula. We can parametrically control the factors affecting the sectional curve using generative components and test various case scenarios. For example, here we have parameters for span of the stadium seating, the number of rows, and degree of the curve at various points, etc. Similarly, the design of the roof of the stadium can be carried out parametrically, as we'll see in the case of Francis Crick Institute. We can collaborate on models simultaneously with integrated BIM workflows. Here we see the example of an underground train station. The roof of this station was designed using GC extension of EcoSim Building Designer, and the complete underground station was designed using different modules of EcoSim, like architecture, structure, and MEP respectively. So effectively, the design of this entire project was carried out by using a single solution, and that is EcoSim Building Designer. Here we have a very conceptual model of a boat bridge along the terrain of the ocean. As you can see that we have created the design parameters for dimensions like height of the bridge, width of the bridge, and side offsets of the columns along the edge. We can go ahead and create similar parameters for diameter and spacing of the columns. The interesting thing to note here is that we can dynamically control the contours of the terrain using control points, and the height of each column updates itself accordingly. Let us go through some case studies. Art Science Museum is an iconic project of Singapore by Arup. As we discussed in the previous part, that it is easy to conceive such structures, but the real challenge lies with the delivery of coordinated GFC drawings. The use of a parametric design tool becomes imperative in such cases, and Arup used generative components for optioneering and StatPro for structural analysis. Francis Crick Institute is an award-winning building designed by HOK and PLP Architecture. The roof of this building is a doubly curved structure, which is a direct response to the layout of the building blocks it is covering. There are two section profiles of the roof along the north and south blocks of building. The origin points of the sweep sections have been derived directly from grid intersections. The path curves of the sweep sections are concave in nature, resulting in a doubly curved roof for both section profiles. The intersection of roof surface and planes results in the centerlines for roof structural members. And then again we divide the surface into parametric polygons which act as placeholders for photovoltaic panels or other customized roof panels. Here we have created the variables for all the design parameters and the coordinates of the control points. Now if we perform the transactions of the sweep profiles, you will see the base surface for the north block roof. And we repeat the process for the south block roof as well. Now as we saw in the previous part of this series, that we can simply move the control points to change the degree of curvature of the surface. But if we create design parameters for the coordinates of control points, then we can simply change the values of those parameters rather than manually moving the control points. Defining these design parameters needs careful planning, as we need to decide what all factors are crucial to our design intent and up to what level of detail we want to control our design parametrically. For example, in this case, we'll be having tapered end profiles for stainless steel structural members at the edge of the roof. The angle of these tapered end profiles is going to be parametric. We divide the surface by intersecting the planes based on the structural grid, and these intersection lines act as center lines for our linear structural members. We'll be having various types of roof panels like skylights, photovoltaic panels and solid panels, etc. Here we have color coded the panels based upon their types and degree of curvature of the surface at their location. As the divisions expand in size at the top curvature of the roof and reduce in size at the acute transition angles. We can also export the panel areas and types to a spreadsheet like Excel and apply some conditional formatting to distinguish various kinds of panels and their areas. Conditional formatting can be based on various parameters like amount of exposure to sun, inclination angles of the panels, areas of the panels, or panel types, etc. Like here, we have applied all these conditions separately to north and south block panels. And finally, we translate these divisions into our customized steel structure members. We can create a detailed component and replace it with the placeholder polygons. Thus, we have a detailed design suitable for fabrication drawings. Then we have the Luxology rendering engine embedded into Ecosystem Building Designer, which enables us to generate some photorealistic renderings. Please see some samples. One Blackfriars is one of the most challenging structures being constructed in the world today. Use of generative components has immensely helped in the following ways. We can describe and analyze the complex form of the tower and its panelization. We can quantify all the panel characteristics in order to test them against industry criteria. It is possible to study all conditions of a particular detail and to rationalize this to a minimum number of variants. We could also test ventilation results for all apartments by quickly varying the parameters. We could quickly quantify overall proportions of solid to void for the whole building for SAP calculations and building regulations. The team working on the project could respond swiftly to client requests for information on areas or quantities of materials. It was possible to quickly transfer data within the design team, in particular the structural engineer, allowing him for a highly interactive design development of the space planning and the structural grid. The team working on the interiors could quickly study alternative design solutions for the random internal panelization and color gradation across the whole tower. There are many such projects in the world which have benefited from the use of generative components and leveraged the power of computational BIM. These are just a few examples. Thank you so much for your time.